Next up is a panel focusing on how biochar production and use can help beyond carbon sequestration, including reducing methane emissions from manure management, reducing fossil fuel energy generation, and reducing the use of chemical fertilizer production and use. And this panel will be moderated by Danielle Sierra, who is Puro's Business Development Director for the Americas. Danielle, the floor is yours.
Thank you very much, Kathleen. And because we're some minutes, starting with delay, I want to get directly to the presentation of the speakers. I want to have the opportunity at the end of the session for the audience to be able to raise the Q&As and to have a more conversational style of discussion after the speakers present their slides. So if we can start with Brendan, that would be great. And Brendan, the floor is yours.
Hi, thanks for having me. My name is Brendan Harrison. I'm a PhD candidate at the University of California, Merced, and I'll be sharing our research on biochar composting as a climate negative solution for dairy manure management. Next slide, please. So methane is a powerful greenhouse gas with a global warming potential 28 times that of CO2, and it's critical that we reduce methane as soon as possible as we transition away from fossil fuels. So first, I'd like to give some background on two important recent methane reduction goals. The first is the Global Methane Pledge that was signed by about 100 countries last year at COP26, and that requires a 30% reduction in methane by 2030. The second is California's short-lived Climate Pollution Reduction Law, or SB 1383, that mandates a 40% reduction in methane from dairy specifically by 2030. And because livestock are a leading source of methane, both of these laws will require governments to take significant action to mitigate methane emissions from animal agriculture. Next slide, please. So the dairy industry in particular is a large source of methane emissions, especially in dairy-intensive regions such as California, where we conduct our work. About half of California's methane emissions come from dairy, with 25% coming from dairy manure. And this is largely due to intensive management practices at feedlots where manure is stored in lagoons or stockpiles, which are both large sources of methane emissions due to the low oxygen conditions in these environments. Next slide, please. So farmers can reduce methane from manure through several management strategies. One effective strategy is by constructing anaerobic digesters that capture methane emitted from anaerobic lagoons for energy production. So basically, liquid manure is stored in large lagoons that are covered, and gas is captured and used to generate electricity. So this method often involves separating manure solids from the liquid portion of manure that flows into the digester. On the right here is a photo of solid dairy manure being separated from the liquids that flow into the digester. So this separated solid manure is often stockpiled into very large mounds until it can eventually be spread out onto fields, but these stockpiles generate large amounts of methane. So composting this manure solid reduces methane relative to stockpiling, but compost can still be a significant source of methane due to anaerobic hotspots or low oxygen hotspots that can form in a compost pile. Some studies have tested a method called biochar composting, which involves composting organic material together with biochar. And evidence suggests that the high porosity of biochar can improve compost pile aeration, increasing oxygen and reducing methane emissions. Despite its potential, this technique had not been tested before in a full-scale trial at a dairy farm. Next slide, please. So to address this research gap, we asked the question, does adding biochar to composting dairy manure reduce methane emissions relative to compost without biochar? And we answered this question by conducting a full-scale composting experiment on a dairy farm. Next slide. We also asked the question, how does the life cycle climate impact of biochar composting compare to composting or stockpiling dairy manure? And we answer this question by creating a life cycle assessment model, which basically sums up the net climate impact of each stage of manure management and use. Next slide. So for our biochar composting experiment, we measured CO2, nitrous oxide, and methane emissions daily from 2 dairy manure piles, one with biochar, added at 6% by mass, and one without biochar. And the biochar we used in this study was created from forestry waste that was produced through gasification at 900 degrees Celsius. And we also measured weekly physical and chemical properties of the compost pile, and the experiment lasted for 5 weeks. Next slide. For our life cycle assessment, we modeled the net climate impact for managing 1 metric ton of dairy manure through either biochar composting, or stockpiling. Our system boundary begins with raw feedstock transportation and ends with amendment application to soil. We incorporated our emission data from the composting experiment along with literature data. We also exclude ecosystem impacts like soil nitrous oxide emissions or changes in plant biomass due to a lack of biochar compost field experiments. Next slide. So moving on to results, these figures show cumulative methane and CO2 emissions from biochar composting. As you can see, biochar composting reduced total methane by over 80%. And differences in CO2 emissions were not significant, although biochar had less CO2. And there were very low nitrous oxide emissions for both piles throughout the entire experiment. Next slide. Here are our results from our life cycle assessment, modeling climate impact over 100 years from biochar composting, and stockpiling. In this figure, each bar is a different stage of the manure management process, and anything below the black line is a sink of emissions, and anything above it is a source. So as you can see, biochar composting had the lowest climate impact with negative 535 kilograms of CO2 equivalent for each ton of manure managed, while composting had negative 194 and stockpiling had positive 102. In addition to reducing composting emissions, which are shown in blue, biochar composting also enhances carbon sequestration, shown in black, due to the high carbon stable biochar that we add to it. And producing biochar is also often a way to produce renewable energy, which was the case for the biochar used in this study. And this adds to biochar composting's climate benefit. And this is shown in green in this figure. Next slide. So when modeling climate impact in the short term over the next 2 decades, and only accounting for direct emissions, so no avoided emissions, biochar composting is climate negative, whereas composting and stockpiling are net sources of greenhouse gases. And this is a significant finding as we work towards managing agroecosystems to be a net sink of emissions rather than a net source. Next slide. So using results from our life cycle assessment, we also estimate the role that biochar composting could play in helping to meet methane reduction goals. So again, California's SB 1383 law requires a 40% reduction in dairy methane, which comes to 9 million metric tons of CO2 equivalent every year. And this is marked in this figure by the red dotted line here. If California primarily uses anaerobic digesters to meet this goal, which is their current strategy, they would need a total of 725 digesters. And this is unlikely because there's only 799 dairies in California that are large enough to house anaerobic digesters. On top of this, digesters are expensive and they can be logistically challenging to engineer, so high adoption rates may be unlikely. If dairy manure solids that are separated from these digesters are biochar composted instead of stockpiled, the state could meet its goal with only 598 digesters due to the additional methane reduction we're getting from biochar composting, which is much more feasible. And finally, the state's herd size, so the number of dairy cattle, is actually declining by about 0.5% every year, and there's different reasons for this. If this is increased to 1% each year, which could happen due to changes in consumer behavior, for example, and manure solids are biochar composted, the state could meet SB 1383 with only 483 digesters. This would allow the state to meet the goal without relying on a very high digester adoption rate by farmers. Next slide. So we also take a look at how biochar composting can help the dairy industry comply with the global methane pledge. If biochar composting is used to manage separated solid dairy manure at intensive dairy farms globally, so farms with at least 100 cows, the dairy industry's technical greenhouse gas mitigation potential for manure nearly doubles, increasing from about 150 teragrams of CO2 equivalent per year to about 300. The dairy industry's methane mitigation potential also increases from about 4.5 to 6.1 teragrams of methane per year. And to give these numbers some context, these are maximum technical mitigation potentials for the dairy industry. So they don't include things like economic or social barriers. So this means that the economic mitigation potentials will certainly be much lower, but still biochar composting greatly increases the maximum potential while being a relatively low-tech, cost-effective strategy, especially since dairy farmers could likely sell biochar compost at a premium. However, the rise in dairy consumption in developing countries is actually predicted to increase methane by about 4.5 teragrams per year, negating much of the benefit of mitigation practices. So a reduction in dairy consumption in developed countries, along with strategies targeting methane from manure and enteric fermentation, or cow burps, will likely be needed for dairy to play its role in meeting the global methane pledge. Next slide. So to conclude, we show that biochar composting is an effective complement to anaerobic digestion, creating a system where methane is reduced from both liquid and solid manure. Biochar composting is a powerful, untapped, natural climate solution with multiple climate benefits. And finally, mitigation strategies alone will likely not be enough to meet regional and global methane goals. And so developed countries may need to reduce dairy consumption to offset increases in dairy consumption in developing countries. Next slide. I'd like to acknowledge and thank my co-authors, the UC Merced Biochar Research Group, the Riles Agroecology Lab, Align Digesters, Philip Verwey Dairy, and the California Strategic Growth Council for funding this research. Next slide. And if you'd like to learn more about our study, it was published in Environmental Science and Technology earlier this year, and it is open access as well. And thanks, and I'll take any questions.
Hi, Brennan. I think we're going to take questions at the end.
Sounds good.
Yeah. Jake or Molly, who do we have lined up next? I know we had some issues with Jacek. So is that all fixed? Okay, we're going to go to our next speaker, Santanu. Are you there? Okay, and then
yes.
Brendan, you can hit the leave. Yeah, perfect. Thanks. All right, Santanu, would you mind introducing yourself? And
can you hear me?
Yes.
Hello all. I am Santanu Bakshi from the Bioeconomy Institute, Iowa State University. So I am my bioenergy platform to use biochar as a soil amendment using soil health, water quality, and carbon sequestration. In a recent project, so we are working with biochar and zeolite to capture nutrients from the swine manure and use the nutrient and calculate the nutrient use efficiency from there. So today I am going to talk about that topic a little bit, using biochar and zeolite to recycle phosphorus and nitrogen from swine manure, an integrative approach. Next slide, please. Swine manure can be utilized as a crop fertilizer. So it is very inexpensive, around 4 to 8 cents per gallon, and it has high nitrogen, phosphorus, and potassium fertilizer value. And from the Iowa statewide analysis, it indicates that around 30 to 40% of the nitrogen and phosphorus for crop fertilization are supplied from this swine manure. And around 75% and 60% of the state's available manure, nitrogen, phosphorus are coming from the swine manure. So now swine manure has a more than 1 billion price tag in Iowa. Manure from the swine fishing burn has an average nutrient value around $30 per 1,000 gallons, considering it has around 10 to 15 pounds of phosphorus, 20 to 30 pounds of potassium, and around 40 to 60 pounds of nitrogen per 1,000 gallon of manure. So manure is the total phosphorus is varied between animal species, age, and diet. And the proportion of the organic portion, inorganic portion, and the water-soluble phosphorus in manure, it varies greatly. So the problem is, to separate out the organic phosphorus and the inorganic phosphorus, and the liquid portion and in the solid portion. Since phosphorus, it moves as a colloidal particle, so it moves in the solid part of the swine manure. So the next is, that means if it has a more than 90% of the liquid part in the swine manure, so you have to extract the solid part of the manure, and then you can extract the phosphorus. So extracting nitrogen is not that problem, but extracting phosphorus is challenging from the swine manure, since it has more than 92% liquid part in the manure. Next slide, please. Yep. So manure has several issues. So where the manure stored in the fishing burn, so they have several issues with the loss of ammonia and different source of phosphorus, and also manure transport is another problem. So it can replace inorganic fertilizer, but it has several issues with the nutrient loss into the water drainage. It releases ammonia and H2S gases, and also it has very low C/N ratio. So liquid manure application cost around $0.017 to $0.018 per gallon, plus around 0.2 cents per gallon per mile of the manure is transported. So that means it does not sound too much, but it generally means that the manure nutrients never travel around 3 to 5 miles radius from the farm they are excreted on. So for the large farm, this means that the nutrients concentrated around the facility. This has led to the over application and keeps farmers from getting the full economic value of the manure. Also, the United States Environmental Protection Agency, they estimated that around 15 to 17% of the greenhouse gas emissions in the atmosphere are associated with the animal manure management in the United States agricultural sector. Next slide, please. So why are biochar and zeolite considered in this study? So both biochar and zeolite, they have unique surface properties. They have high porosity, macroporosity, high surface area, and high absorption capacity, and they can both act as a sponge towards crop nutrients like nitrogen and phosphorus. So left side, there are some pictures of the biochar and the scanning electron microscopy pictures of the biochar, and the right side, there are pictures of the zeolite framework structure. So for the biochar, partial oxidation condition of autothermal pyrolysis, it converts biochar into a good sorbent material of phosphorus and nitrogen. So we have 2 published manuscripts mentioned below if anyone is interested to read it. So we showed in this manuscript that it has a very good phosphorus absorption capacity, and in another manuscript we have shown that it can act as a slow release nitrogen fertilizer. In the right side, the zeolite structure, so substitution of one silica ion with aluminum ion causes one negative charge, and that negative charge can be utilized to trap nitrogen ion, especially ammonium, from the swine manure. Next slide, please. So what our project goals were how biochar and zeolite can be used to build an integrated system that provides both economic and environmental benefits in the animal agricultural industry. So in the schematic diagram, we have shown that in the manure, liquid manure, which has ammonium and phosphate ions, we can trap into in biochar and zeolite and make it a solid fertilizer, and then we can make it apply into the agriculture. So that will solve the liquid manure transportation problem, and also that can solve the gaseous emission like ammonia, H2S gas emission problem. So our specific objective was to address the biochar and zeolite or mixture of two in an integrated approach to achieve a low-cost nutrient fertilizer consist of nitrogen and phosphorus from swine manure. Next slide, please. So, okay, so our total innovation exploration. So what is that pyrolysis bioenergy biochar platform? So we proposed an integrated bioreactor system from where we, in the center, there is a picture of a swine. So we can collect the manure, livestock manure, and then we can use biochar and zeolite, and we can also employ the anaerobic digestion to produce recycled nutrients. In the other hand, they can create, reduce the odor control, reduce the GHG emission, and it can mitigate climate change. And also recycled nutrients, we can use it in the crop agriculture, which can reduce the nutrient loss, reduce the synthetic fertilizer use, and improve the water quality and build soil quality. And we can create more renewable fuels, energy, and products, and we can improve the economic activity. So overall, the proposed project will examine the potential of an integrated bioreactor system to reduce emission of the GHG to the atmosphere and recycle nutrients from manure for use in crop production, reducing nutrient loss to water bodies and to the water atmosphere. Also, this proposed system can present an opportunity to improve the economical and environmental performance of integrated crop and animal agriculture. Next slide, please. So the materials. So we have used the swine manure, pH of close to 8, and we centrifuged to separate the liquid fraction, and the manure contains around 250 milligram per liter of ortho-P and around 3000 milligram per liter of ammonium nitrogen. We have used 2 different biochars. One is the iron pretreated and another was the iron control biochar. So the iron biochar pH was around pH 5.4 and GPC 0 point charge is around 4.8. And the control biochar has a pH of around 9.2 and 0 point charge is around 8.5. And we have used a GSM-5 zeolite, which has a silica to aluminum ratio around 30:1. Next slide, please. So iron, so these are some data, these are some results I'm going to present that iron and control biochar, they have different phosphorus absorption capacity. So the orange ones are the iron biochar and the blue ones are the control biochar. So now you can see that iron biochar absorbing more ortho-P from the aqueous solution rather than the manure. whereas the control batch absorbing more phosphorus from the manure rather than the aqueous solution. So the results are, the iron batch results show that the iron batch was less efficient removing orthophosphorus from manure than water, whereas the control batch was more effective removing orthophosphorus from manure than water. So this shows that the contrasting properties of the biochar we have used in this study. Next slide, please. So when we did the desorption study, virtuously the iron biochar slowly releases ortho-P during the desorption study. So in the left-hand side, you can see the iron biochar, and the right-hand side is the control biochar. So the dark red is the absorbed amount, and the light red color is the dissolved amount. So you can see that the iron biochar hold more phosphorus and release less phosphorus during the desorption study, whereas the control biochar has released more phosphorus during the desorption study. So we have used the Melic 3 solution for the desorption study. Around 10 to 20% of the dissolved ortho-P dissolved from the iron biochar, and around 35 to 80% of the dissolved ortho-P dissolved from the control biochar. Next slide, please. So we did a column leaching study, and we did the breakthrough curve of that of the phosphorus absorption. The left hand side, this is the plot of CT by C0 different versus number of manure addition, and in the right hand side is the phosphorus absorption versus volume of manure added. So the blue is the control biochar and the red is the iron biochar. So we, in the right hand side, you can see the absorption capacity is around 33 milligram per gram of phosphorus using iron biochar, whereas control biochar is also showing around 29 milligram per gram. So we have used the Melic 3 solution again for the desorption study, and we found around 76% of the absorbed ortho-P dissolved from the iron biochar, whereas around 85% of the absorbed ortho-P dissolved from the control biochar. So from this study, this study suggests that the phosphorus absorption is happening in the high colloidal particles with the biochar. So when we did the desorption study, that colloidal particle together with the phosphorus came out into the solution. Next slide, please. Zeolite can also absorb ammonium nitrogen, but less effectively than biochar. So in this study, we did iron biochar, control biochar, and the zeolite for the ammonium nitrogen, and we have shown that the iron biochar is absorbing more ammonium in the aqueous solution than the manure, whereas the control biochar, there is no significant difference, and whereas the zeolite can absorb ammonium but less compared to biochar. It absorbs more ammonium from the aqueous solution than the manure. So this study suggests that the specific absorption, cation exchange site absorption, is happening in the zeolite rather than the biochar, whereas the biochar has more pore space or surface functional groups absorption or the cation exchange site absorption compared with the zeolite. Next slide, please. So again, for the ammonium desorption, we did the iron biochar and control biochar. And biochar shows slowly release of the ammonium nitrogen during the desorption study. So we have used the 2 normal KCl solution for the desorption study. And desorption rate decreased as the manual load increased, and also the high manual loading facilitates the ammonium absorption, specifically in the colloidal portion. So that means with high manure, the desorption rate decreased because the ammonium goes into the colloid part. So iron biochar dissolve a little bit higher ammonium compared to the control biochar. So left hand side is the iron biochar, right hand side is the control biochar. So this study shows that the iron biochar, control biochar has a more absorption capacity of the ammonium nitrogen compared to the iron biochar. Next slide, please. Next slide, I have shown that zeolite can also release ammonium during desorption, from the manure and from the aqueous. So the yellow is the desorption and the orange is the absorption. So from the zeolite shows less desorption from the manure rather than the aqueous. So here also we can say that desorption rate decreased as the manure load increased, and also the high manure increases the percentage of colloids, and which facilitates the absorption of ammonium. So that means in these two slides we have shown that both biochar and zeolite can absorb ammonium and can slowly release ammonium during the desorption study. Next slide, please. So if we compare the overall system of the biochar and zeolite, so we have shown that zeolite overall improved the ammonium absorption efficiency. So we did the breakthrough curve after 15 sequential additions of 10 milliliter of liquid manure, the 1 gram biochar and centrifugation, and we did the breakthrough curve. So for the iron biochar system, zeolite increased the absorption around 82 milligram per gram, or 82,000 milligram per kilogram. For the control biochar system, zeolite improved around 58 milligram per gram, or 58,000 milligram per kilogram of ammonium compared to the biochar system alone. So, and we did the desorption from there, and we found that low desorption from the system of ammonium nitrogen using 2 normal KCl solution. So this slide suggests that zeolite can improve the overall nitrogen absorption and low desorption of ammonium after the total system analysis. Next slide, please. So in this slide, we did the XRD analysis of the material we recovered after the breakthrough curve, and it shows the formation of the struvite mineral into the biochar surface. So there are 4 samples here: control biochar manure, iron biochar manure, control biochar, and iron biochar. So in both the control biochar manure and iron biochar manure, we have found a struvite formation of ammonium magnesium mineral with the phosphate, and we attribute that this is the main reason that ammonia and phosphate is getting stabilized into the biochar system. With the magnesium ion, so swine manure has huge amount of magnesium and calcium itself, so magnesium is coming from the swine manure. Next slide, please. So in the next slide, we have shown that the SEM scanning electron microscopy energy specific spectra, it also shows that a significant magnesium phosphorus nitrogen association in different points for both the iron biochar and the control biochar. So in this study, we found that magnesium rather than iron is making complex with the phosphorus and nitrogen onto the biochar surface, rather than forming an iron phosphate complex on the biochar surface. So XRD and SEM analysis proves that a successful formation of the struvite mineral onto the biochar surface to stabilize the nitrogen and phosphorus. Next slide, please. So overall, our recent study shows that the biochar and zeolite can recover phosphorus and nitrogen from swine manure. So in the schematic diagram, we have shown that in the manure, if we add the biochar and zeolite, and after that, if we do the scanning electron microscopy and the XRD, we found significant association of nitrogen phosphorus with magnesium, and some iron phosphorus with phosphorus, some iron phosphorus association without any mineral formation, some maybe in the amorphous phase. So nitrogen and phosphorus can be stabilized into the biochar and zeolite system, and we can recover that phosphorus and nitrogen from the system to use as a slow release fertilizer. Next slide, please. So overall conclusions. So nitrogen and phosphorus adsorption capacities from manure largely depends on the biochar and zeolite surface properties. So another one is iron impregnation of biochar overall improved the phosphorus adsorption, but not nitrogen. So for the nitrogen absorption, we need a combined system of the biochar and zeolite. Manure magnesium is predominant over iron in biochar for the phosphorus association. And the nitrogen and phosphorus loaded biochar and zeolite can be used as a slow release fertilizer, providing nitrogen and phosphorus to the crop plants. Next slide, please. So acknowledgement, so funding for this work from the USDA and IFA, we recently granted this year. So, and also we wish to thank students, some of our undergrad students, for their assistance in the lab. And we also thanks Warren and Dapping in our material science department for assistance in the SCMEDS and the XRD analysis. So I would like to stop here and can accept questions from you if you have any. Thank you.
Okay, congratulations, Santanu, on a very nice presentation. And I would like to start making a couple of questions to you and then to Brendan, but I wanted to make sure from our panel, I'm just receiving confirmation right now that the third speaker that we have on for today, it's not going to be able to present because of audio issues. I believe that we can post his contact information as well, and he's mentioning here that he might be able to record his presentation to share it with the rest of the audience. So hopefully we can do that as soon as possible. But going back to both of the presentations we just heard, and I want to start with you, Santanu, since we have your information fresh. I think all the information you presented is extremely interesting, and I think it might be very complex for the non-scientific oriented audience. But I want to get your thoughts on why do you think these studies that you conducted and the results coming out of them, what do you think is the relationship with those studies and climate mitigation potential of biochar?
Yeah, obviously. No, that's a very good question. Thank you. So we are trying to capture, we are specifically in this project, we are working to valorize the swine manure. Swine manure has a huge source of nutrients, around 4,000 milligram per liter of nitrogen and around 1,200 to 1,500 milligram per kilogram of phosphorus. So farmers are applying this swine manure directly in the agricultural fields close to the end of the fall semester before the winter to get ready for the next year field. Now the problem is most of the nutrients, they are not utilized by the croplands. They are going into the underwater bodies, and ammonia and H2S and also methane that goes into the atmosphere. So our main aim, our main goal for this project is to reduce that nutrient loss into the water body, reduce the greenhouse gas emission into the atmosphere, and utilize as much as possible of the nitrogen and phosphorus in a solid form. Now, in my earlier presentation, I also mentioned that liquid manure transportation is a huge problem. You cannot transport the liquid manure 100 miles or 150 miles. So farmers, they have a tendency to apply the liquid manure in a nearby fields, that means from where the manure is excreting on, maybe maximum of 10 to 15 miles radius. That means that manure is getting concentrated in that area years after years and after years. If we can convert this liquid manure into a solid particle-like thing, like solid nitrogen fertilizer or solid phosphorus fertilizer, it would be easier to carry, and the farmers can carry over 100 miles or 150 miles of the fertilizer from one place to another. So basically, we are saying this is a novel manure management program to give ecosystem service, to reduce the GHG emission, to increase the soil fertility, and also economic and environmental impacts.
Definitely.
So yeah, so that's why we are saying it's an integrated pyrolysis biochar bioenergy platform to create the bioreactor.
Great. And I think that some people might see it initially as a waste management solution only, which it is a waste management solution, but not
Yes.
only. This issue of increased fertility because of the nutrient uptake can help to displace fossil-based fertilizers and also help on GHG avoidance on that side. So I fully agree with you that there is a clear connection to climate change mitigation by doing this. It's always that it's not evident. You need to be able to present the case, and I'm fully confident that this is a very promising solution.
Yeah, and I just want to add in my previous presentation, in our previous presentation, Brendan already showed that biochar can reduce the methane emission close to 80%. That is actually very helpful. That means if you can reduce the methane, though methane is a powerful biogas, you can produce bioenergy from there. But in the stockpile or in the manure burn, where they are piling the manure years after years, they are creating a lot of methane. So if you can reduce the methane, that is the important factor. That means biochar can reduce the methane. Also, biochar can increase the nutrient cycling. So we have a win-win scenario.
Yep, definitely. I want to pick one of the audience questions to you that it's quite technical, but I think it's interesting. It's coming from Nadat Siv asking, could you explain the method to produce the iron biochar? Biochar with pH of 5.4 is very interesting.
Yep. So we have a patented autothermal pyrolysis plant at the Iowa State University, led by Dr. Robert Brown. So we do a partial oxidation condition. We blow a little bit air during the pyrolysis technique. And if you want more information, I can share the website. You can find more information there. But the autothermal pyrolysis needs a little air for the partial oxidation. So we treat the biomass, corn stover biomass, with a iron 2 sulfate, which is from the steel production byproduct. So we impregnated that iron 2 sulfate in the biomass and then soaked for 48 hours. And then we do the pyrolysis. At the end product, we noticed that the iron 2 oxidized to iron 3 due to the partial oxidation. And iron 3 mineral we can find in the biochar. That iron 3 mineral is very helpful to absorb the phosphorus and to make a stable iron phosphorus compound. Since iron 3 is there, during the hydrolysis of iron 3, it produces one proton ion, one hydronium ion, H+ ion. So that is the reason that iron causes the pH reduction close to 5 compared to the control corn stover biochar. So it's totally the iron chemistry.
Thank you very much, Santanu. And now I would like to ask a question to Brendan. And correct me, Molly, if I'm wrong, but we do have Brendan here. Yes, great. Brendan, congratulations on your presentation. And I want to start with the mechanics of why the methane reduction happened. If I understand your presentation correctly, you were saying that there is an increased aeration and therefore increased oxygen content. And because of this, there is a decrease of methane. Can you talk a little bit more about that?
Right, that's exactly right. So what we see is that because biochar has this porous structure, it really increases the porosity of the compost system, which increases oxygen. And just for, if those of us in the audience don't know this, methane is produced when there's not enough oxygen in a system, when there's very low oxygen. So it's kind of as simple as if we can increase oxygen, we're not even going to be producing methane. Also, once methane is produced, it can be absorbed inside of the pores of a biochar particle. It can then potentially be consumed. So there's actually microorganisms that consume methane. And we're actually following up this experiment where we're actually diving into the microbial systems and looking at which microbes are present, so we can kind of tease this question out a bit further. You know, we have microbes that produce methane, we have microbes that consume it. How is biochar influencing these communities? So we're actually looking into that further. But as far as the dominant mechanism, yeah, it's increasing oxygen. Methane is not being produced as much.
Very interesting. And I also wanted to ask you about the paper you published in the journal you mentioned at the end of the presentation. How has the feedback from the scientific community been?
Generally, quite good. A lot of the feedback we are taking into consideration, and we have several follow-up experiments to this. One that we're very excited about is we're actually using this material. I mentioned that there are not too many studies, at least long-term field studies, using biochar compost as a fertilizer and then comparing it to just biochar or just compost. So we're actually in the process of conducting a field experiment and using this, looking at how is this affecting the soil system? Is it, giving farmers a water benefit, a nutrient benefit, a harvest benefit? Because we want to optimize the uses of these organic resources, right? We have materials that can be created into biochar, and we have we have manure, right? But with the optimal ways of transforming these organic resources into organic fertilizers.
Okay, and we have something that I have always wanted to have in a panel, which is a question from your fellow panelist, Santanu. He's asking, question to Brendan as a follow-up of the question before. Does biochar reduce the methanogenesis process? Does biochar increase acetic acid production instead of methane and carbon dioxide?
So we actually, in this particular experiment, this was a large-scale farm experiment where it's kind of like a proof of concept, right? We're not as much looking into the mechanisms, but we are following this up with a laboratory experiment where we're really teasing out the mechanisms. So at this point, we don't know, but we are looking into exactly how biochar is transforming the composting process. We're looking into the microbes and also the biogeochemical interactions between biochar and manure. So at this point, I can't say for sure. I think it's very likely that biochar is reducing methanogenesis because of the oxygen content in the pile is increasing a lot. So that has to be part of it, but I don't know for sure other than that.
Yeah, and a related question coming from Silvia Skosafava. I'm sorry for botching your last name, Silvia. But she's asking, would it be worthwhile exploring inoculating biochar with methanotropic microbes to increase methane abatement in the manure biochar system?
Yeah, I mean, I actually, we have an undergrad who proposed the same thing, and I was kind of taken aback by that. It's possible. I guess I mean, so there's 2 points, right? If we increase oxygen in the pile, that might not be necessary in the first part. We don't want to over-engineer systems because that increases cost, and we want to make things as cost-effective for farmers as possible. However, we should try it, right? Like if we're getting dramatically more or bigger reduction in methane, then maybe it's worth it, and maybe there's incentives to start to cover the cost of that.
Okay, and one last. Sorry, I missed that one.
Oh, I just said I haven't seen people try that before, so we have to try everything.
We do, I agree. And one question from me, coming out of your very interesting information you presented of the, the biogas investment that you would need to have in order to take advantage of this. You were saying that it's very costly in terms of capex. Is there another reason that you would think different from investment that would preclude the, using this as an alternative source of energy at the scale that is needed? And I think you were kind of hinting towards that in your presentation, but I want to go deeper into what you think about it.
So just so that I'm understanding your question, you're talking about barriers for anaerobic digestion?
Yes.
Yes, there are several. First of all, we have to acknowledge that anaerobic digesters are very good at reducing methane from intensive systems. They are quite expensive. There's a large initial investment that farmers have to make. In California, we have some subsidies for this, but even still, it is high. And dairy farmers right now are struggling in California, specifically with the drought and rising costs. So they might not want to do this, right? So it is a huge barrier. You don't have to have an anaerobic digester to biochar compost, but we're kind of proposing this system where you can have both at the same time, and that's how you maximize methane mitigation. You don't have to have that. You can do it on manures that you have on your farm. But you do have to purchase biochar, which is an investment. But we work with economists on this project as well, and we do see that if you're able to sell this biochar compost, you're able to make a profit. So you invest in biochar, but you're selling the biochar compost, and you're making a profit off of that. So it is cost effective. But the key here is that we have to kind of prove that biochar compost is the optimal organic fertilizer in these systems. We have to show that we have to expand the market for this, basically, if that makes sense.
Yeah, I agree. We still have a chance for one last question, but before that question, I do want to mention, and here I got a note from Jacek, and Jacek, I'm going to butch probably your first name and your last name. It's Jacek Chmielewski. He wanted me to mention that he was not able to make the presentation. He will try to record it, but he wanted me to mention the project in Puerto Rico that it's BRI, Biorestorative Ideas, doing biochar out of invasive bamboo for coffee growing. And I would encourage everyone in the audience to look into that project. It's in the Puro framework, and I believe it's very promising. And I don't know if Brendan is still with me. We still have 2 more minutes. Yes, great. I was trying to think about the scale of the biochar needed. First, to achieve, this very interesting idea you had of the climate ambitions of the state of California for the 700 and something dairy facilities. What would be the scale of the amount in metric tons of biochar needed to abate this methane? But of course, if you can think of only one, that can give us, an easier way to think about this scale needs into the future.
Yeah, well, the nice thing about this system is that you don't need a lot of biochar. And we actually see that sometimes when you have higher biochar application rates to manure, you get unintended consequences. Sometimes we see higher methane emissions when you have higher biochar application rates, like 20% by mass, for example. There's several reasons for this, but to get at your question, in our study, we used about 5 or 6% biochar application to manure. This is relatively small, and especially in California, we have so many almond orchards in the Central Valley, especially. There's so much biomass. And we actually have another law, I didn't mention this, but in 2025, burning of biomass on farms is going to be banned. So we have this huge influx of biomass, and farmers have limited options for managing this. Traditionally, this is just burned on site. We're looking into mobile pyrolyzers, bringing them to orchards. This is cost effective because you don't have to move large amounts of biomass, raw biomass, to a central facility. But we also have central facilities that are close to orchards. So I don't have an exact number for the amount of metric tons, for example, of biochar that would need to be produced. But in terms of application rate, it's not very high, which I was impressed by. I mean, we're getting an 84% reduction, adding 5% biochar by mass. That isn't very high. And again, we have a huge influx of biomass coming soon, in California at least.
Okay, well, thank you very much. I think the presentations were incredibly interesting, and hopefully Jacek can send the link to his recorded presentation very soon. And thank you everyone for your questions.
Hello, this is Jacek Chmielewski, and I first of all wanted to apologize for the technical difficulties that prevented me from presenting live. In any case, I am a principal at Biorestorative Ideas as well as Biomass Solution, and I have interest in a couple of other companies that I'm not going to be presenting right now. In my presentation, I wanted to go over several subjects. I wanted to, first of all, cover some of the pyrolysis technology and our selection process. Also talk about feedstock consideration, then about actual project execution and development methodologies, and follow that with example of actual project and subsequent applications for biochar, which would be in soil amendment and PFAS remediation, plus some others. First of all, the idea behind energy and any kind of a value that could be gotten out of biomass boils down to pyrolysis and associated recalcitrance of carbon when the pyrolysis process is actually performed. Staying on the topic of renewable energy and potential, there are opportunities around pyrolysis to generate enough producer gas and efficiently recycle it for thermal use, as well as potentially electrical power use or other thermal uses. In the project that I'll discuss a little bit later on, we also have options on potentially generating some additional renewable power using solar electrical energy. Beginning with the process that we went through to select our pyrolyzer technology, we looked at 4 different categories. First one being micro-sized, typically very much small amounts of feedstock and batch operation. Second one was slightly larger than that, but still small and batch. The third category, which is actually what we landed on, was slow pyrolysis, available for highly distributed and plentitude of feedstocks that are available in the Americas, and continuous. Continuous is very important because there's a component of carbon removal credits that has to be tied to the data collection. In any case, there's also another scale of pyrolyzers that are not yet plentiful, and that's a very large scale pyrolysis, which typically happens to utilize fast pyrolysis, and these would be centralized and draw on high volumes of feedstocks. So Biomass Solution and BRI have landed on the mid-scale pyrolysis. We have selected a primary and preferred OEM supplier that's located in Iowa called RT, and they have quite a bit of fungibility and flexibility associated with their system, which allows for a broad number of feedstocks to be actually pyrolyzed using their technology. As you can see in the slide, there are some technical features of their pyrolyzer. Now, in any pyrolysis or any upvaluing of materials available, feedstock is a really key component. And even within the feedstock that most ideally should be aggregated, the moisture content and the carbon available and other energy-bearing molecules that are within the actual feedstock makeup are also very important. If your moisture in the available feedstock is too high, quite a bit above 50 weight percent, then the availability of that and opportunity with that feedstock is going to be reduced as pertaining to any latent heat that might be left over to generate renewable energy or utilize in some other way. So examples of candidate feedstocks, you can read them below, but obviously bamboo, wood mill, waste of various types of nutshells, crop residues, as well as corn stover, DDGs, and also manure, which was discussed by some other panelists on this particular panel, are really opportune feedstocks, and each one presents a set of opportunities, but also a set of challenges. Now I wanted to jump into various projects that we are executing with BRI, as well as Biomass Solution and other partner companies. So I will cover the BRI project in Puerto Rico called Eureka, which is the invasive bamboo, and that's due for a startup in January of 2023. Also, I'll talk about a third-party operator of an anaerobic digester, but a very interesting project that we help to advise on that utilizes crop residue and is scheduled for startup in first quarter of 23, but that's a pretty unique project. Then we will go over some biomass solution and partners projects in California that will utilize nutshells, and these would be due for startup in third quarter of 23. And then a couple of concepts that are right now in development and evolution, one of those being boiler and gasifier, potential migration to partial pyrolysis or full pyrolysis. And then the last one would be biomass solution opportunities around anaerobic digester, existing dairy and cattle, but primarily dairy anaerobic digester, integration of pyrolysis into that process. So Biorestorative Ideas Project by BRI, Eureka project is located in Puerto Rico, actually on the very western side of Puerto Rico, where a lot of issues are associated with rivers that are basically surrounded by an invasive bamboo species called Bambusa vulgaris. And that project was developed with full support from our team, as well as Puro and Jacek as the LCA provider and assistant in our carbon removal credit generation. In the first phase of the project, which will be started up in January, just coming up next month, we will have no renewable energy generation because the types of bamboo and bamboo species that are going to be utilized here, as well as the age of the bamboo, doesn't necessarily give us enough of the energy. But as we optimize in the second phase, we might be looking at energy generation, because Puerto Rico is challenged with that aspect, especially since it's on the hurricane alley as well. So there are periodic issues associated with weather. And what we think, and our calculations show, that we would have potentially about 6 million BTUs per hour, about 6.3 megajoules per hour, or about 1.7 megawatt hours potential to generate as electrical power. So in development of our project, we took a lot of different drivers into consideration, and we have used a risk-based approach to design our operation, as well as the overall project. But one of our principles is subject matter expert has high degree of expertise in this space. So we developed many different matrices associated with development of risk that could be experienced during both project development as well as the pyrolyzer operation. We also utilized and will be implementing in full our data-driven operation and data-driven compliance software package that will ride along and on top of the RT package, software package that we will have for our project. And this will include feedstock handling, mapping of where it's actually collected. It will have the workflows associated with warehousing, predictive maintenance, calibration of instruments, as well as components in sales, CRM, and ongoing training modules. We are also going to be utilizing our optimizing software for process, statistical process control, which will help us eventually get to phase 1 to phase 2 of our operation, where we can actually generate quite a bit more of electrical power and another revenue source associated with the pyrolyzer operation. And then last but not least, there is a component of the software that incorporates dynamic LCA reporting, which is very important for carbon removal credits, as well as other outputs that we will be sharing with our customers. And this is something that I think is going to be of high importance across this whole industry, as the auditability and availability of data is so important to make the product as well as the carbon removal credits very much secure, believable, and assured. Moving on to the project in Minnesota, utilizing crop residues, which was done by Biomass Solution and third party in an advisory role. This particular project will be generating enough of latent energy because of the actual feedstock that's going to be used, and that feedstock is not very moist. So the interesting thing about this particular project is that actual energy will be used in an adjacent process as thermal energy, not so much electrical power, but as thermal energy. So there will be additional types of credits that might be available coming out of this project, since quite a high number, and in approaching 7 figures will be saved on annual basis by offsetting the fossil fuel energy use in the third party, not a third party, but associated process right adjacent to the pyrolyzer. So the total energy potential will be about 12 million BTUs, or 12.6 megajoules per hour. Next project that we have in development stages right now will be located in California, and it's going to utilize some byproduct nutshells of various nut species. And in the case of this particular project, there will be enough of latent energy available to generate up to 2.9 megawatt hours of electrical power, which is about 10 million BTUs per hour, or 10.5 megajoules or million megajoules per hour. And then this project is going to expand to second phase, which will basically quadruple that electrical energy potential, and located in California and feeding into the California LCFS and CARB requirements. This would be an important aspect of revenue generation. Plus, the biochar that's going to be formed and made out of this process will also be applicable in soil amendment applications, but other water-related applications as well, and PFAS remediation that will be discussed a little bit later on in the presentation. Next point on the agenda was a potential for existing gasifier and boiler migration to either full or partial pyrolysis, which would allow existing facilities to still generate substantial electrical energy, and perhaps as they're starting to get phased out in a lot of areas, and potentially this type of electrical energy is not being looked upon as favorable on a longer time frame, pyrolysis could be substituted and used as an additional technology next door, providing the actual producer with some value adds associated with biochar as well as carbon removal credits. So we think that this is a great potential that should be looked into in the years to come, and it's just now in initial stages of development. This is the last topic I wanted to discuss in this stage of the presentation, and that's the biomass solution anaerobic digester dairy manure value proposition. And this slide is extremely busy, but if you walk through all the different stages in this slide, I think it's pretty self-explanatory, but basically it involves utilizing pyrolyzer as part of the value proposition add-ons to an existing anaerobic digester, where you can have the option of some electrical energy being generated to enhance the low CI score, carbon intensity score power, as well as enhance biogas production by addition of some of the biochar into the substrate stream of the anaerobic digester, and then incorporation of other renewable energy components. And resulting out of that, there's obviously a good quality biochar, which could be applied in many different applications, which I'll discuss in the subsequent several slides. So very busy slide, a lot to digest there, but that's something that Biomass Solution, as well as our partner companies, have been working and developing now for about 2 years. I wanted to spend a few minutes on one of the main applications for biochar that will be produced pretty much out of every one of the discussed projects. And obviously, all the biochar that's going to be produced using the technology is going to have a high degree of carbon recalcitrance associated with it. It will be used in fertilizer application as soil amendment, which I don't want to list out all the advantages, but you can read them here yourself. But there are many different advantages, many different opportunities associated with this particular application. And this is work in progress, and it's supported both by private industry and then heavily supported by the federal government as well. As we go through the soil amendment applications, what is going to be needed to accelerate adaptation or adoption, I should say, and an adaptation of the existing farmer practices? So everything begins with education. I think there's a lot of information available across the academia as well as some private industry, but vast majority of farmers are not very well educated or made aware of the value associated with biochar application. So we think that mid-scale field trials are going to be required on various soil types, as well as a lot of different row crops. Next thing is the federal support, which there's going to be a dedicated presentation, I believe, on December 14th and 15th, associated with the US ENRCS 808-336 practice, which is the biochar as soil amendment application. And then the farmers also has to be associated with this particular practice, and the federal incentive educated on the rewards that they might gain by applying biochar and incorporating biochar into the normal practices. And lastly, but not least, we think that broader consumer education is also required, and that would be on the nutrient value of the actual products that the farmer would actually grow, and the realization that there's a a lot to be gained out of having more nutrient-rich foods that will be produced for consumption. On this slide, I've listed some of the biochar soil amendment climate advantages, and these are also relatively well known in our circles of scientists and developers and technical folks. But there are many. So there's methane and nitrous oxide emission reduction, a lot of fossil fuel usage, offset and footprint reduction. There are also carbon credits and offset credits available, and those are already well established by Puro and their partners. Those actual credits and the methodologies can help the farmer, and certainly realizing some revenue. And then there are a lot of follow-on avoidance credits, as well as long-term, potentially the soil value, the land value itself, and increases associated with that. So many different pluses. I'm almost finished with the presentation here, but I just wanted to show you a little bit of a broad opportunity in other markets, and besides soil amendment applications, which has been shown to be worth over the next 5 to 10 years about $30 billion in the United States alone. These numbers do not include Canada, but there are a lot of other opportunities around PFAS remediation, around phosphorus and nitrogen management, of course, water treatment, wastewater treatment, and lots of other smaller applications. So altogether, I think biochar has pretty well identified around 60 or more high-value applications. So it is a platform material, and one thing I would say is that it's also a material that could be regarded as a new unifier across the political divides in the United States as well, because it provides such broad advantages, not only from a climate perspective, but soil health, the farmer, and obviously it has pretty strong returns if the application is done appropriately, as well as the production is efficient. So many different advantages, and a great platform material. With that, I wanted to conclude. And again, I wish I was able to present to the live audience. But on this slide, you see my contact info and our websites, and encourage anybody interested in learning further about our project approach, the software, as well as methodology, how we go about developing high volume projects and move them to reality. Please visit us and get in touch with me, or in contact via my cell phone, or my email address is given here. Thank you very much, and thanks for your attention, and have a wonderful day.